Thank you. When I was an undergraduate student, I had this idea that the world of functional programming was split into one half of people who like the rigor of static typing, and another half who insisted on the freedom of dynamic programming, on dynamic typing. Yet at the same time, unexplainably, would actually be very happy to confine themselves to an extremely primitive syntax. At that point, I decided I should pursue a career in the statically typed world, because this seemed to be associated with people with principles who like to do things the right way. I figured maybe other people would think I'm like that. While, of course, in reality, I would spend my time hacking on Emacs. So over the years, hacking on Emacs, I discovered that while I like static typing very much, I much prefer it to dynamic typing. When I work in ML, I miss the macro programming facility to let you define domain-specific languages or little languages very conveniently, easily. So that was part of the motivation, a significant part of the motivation behind the design of this language I call Piper, where I basically wanted to have a very simple core with, of course, dependent types, but also a flexible, convenient syntax and seamless macro extensions. Okay, so what does Piper look like? Well, here is just to prove that it does belong in an ML workshop. Here's some example of the syntax. I think you can guess what this means mostly. So, we have algebraic data types, function definitions, we have types, and the types are optional because they can be inferred, the usual stuff, nothing very enlightening here. So, when we want to add macros to a language with infix syntax, and when I say infix, I mean more generally with just a somewhat traditional kind of syntax, you bump into one particular problem, which is linked to the existence of multiple syntactic classes. So you can see it here in an example of OCaml code, where you see there's x equals a semicolon b that appears twice in this expression, once in a declaration position and once in an expression position. And OCaml will parse those two identical pieces of text in very different ways, because once the equal is a definition equality, and in the other one it's a Boolean conditional. So if you have a call to a macro where you have this kind of argument, how is this supposed to be parsed? Well, of course, you don't know without knowing what my macro will do with it, whether it will treat it as a definition, as a declaration, or as an expression, or even something else. So to deal with it, you can simply delay parsing of the arguments. Of course, that's the first option. Another option is actually to have the definition of my macro specify what kind of syntactic classes are used for each of the arguments. But that tends to bind the parser with the macro processing and macro definition in ways I don't like very much. So I figured I should do what a LISP would do, which is another problem. So I basically enforce that the relative precedence of operators is the same everywhere. And of course, that's a feature, not a restriction. So how do I enforce this? I enforce this very easily by just using a very weak syntax, a weak parsing technology. In this case, I use the operator precedence grammar, which was defined fairly recently compared to the Leibniz equality. And the way it works is that you have, basically it works on pairs of keywords separated by some kind of sub-expression, and where the question is basically what do you do with this sub-expression? Do you associate it with the left, or do you associate it with the right? And this choice is made without paying attention to the surrounding context. That's the crucial part that makes it work. That solves the problem that I'm trying to avoid. So I don't need to know whether it's an expression or a declaration, because in any case it will always be parsed in the same way. So this ensures that I cannot define the occamable syntax using this kind of grammar. This is of course nothing new. Abla uses a very similar system. So here's an example just to give you a taste of what it could look like. So you use a table where you say, for example, that left bracket has a left precedence of nothing because it cannot associate with anything on the left, and a right precedence of 1 which matches the one of the right bracket. So because they have the same precedence, they actually combine, they get together. And so when you have the first line here, it will be parsed basically as it is. So here again, it works very straightforwardly. Now, how do I use this in Typer? Well, I use the front end of Typer is structured like that of LISP, which means that the source is read by a reader, it's processed by a reader, which just returns what I call an S expression. Some other people call the S expression the textual representation. Here I use it strictly to talk about the internal representation of the structure. So the main point is that it's a tree that doesn't have any semantic associated with it, because it doesn't know what are the core constructs of the language at that point. So once I have this tree, I actually try to process it and see if it is a meaningful program. And along the way, of course, I will expand the macros. So just like in Lisp, one of the benefits that you can use the reader to parse other things than actual type of program. So if you look at the type declaration I had shown earlier, that defines the usual Lisp type, the way it's read by the reader is exactly the same as the second form you have here, with all parentheses, etc., etc. So if you like to write parentheses for some obscure reason, you can feel free to do so. The only difference with Lisp is that parentheses are not significant, they're only used for grouping. So, how do I extend the syntax in Typer? Well, this is not a main focus right now of the language, so I have very primitive facilities to do that, which is just to define the precedence of operators. So with those 3 lines, for example, that lets me define that this syntax here is equivalent to that syntax there. And that it just basically gives me syntactic sugar. The main point here is that the extension of syntax and the definition of macros is completely separate. So this doesn't actually define any kind of if conditional, it just defines some equivalent syntax. So if I want to have such a thing as a macro, and so that this syntax can be used for the usual if conditional, I want to define a macro. So, how do I define a macro? Well, I define it just as is common in Lisp, and actually here you'll notice that this is defined really in the Lisp style, not even the scheme style. So this is one of the things that will need to be fixed. But, so the macro is basically a function that takes a list of arguments represented as S expressions, and then builds an alternative S expression to use as the body. One thing to note here is you see this case expression inside the quote, and you'll notice that it uses a fairly normal and familiar syntax. Even though this is actually not an expression of Typer, this is just a bunch of an S expression data that is passed to the quote macro to actually build up some real expression. And here we use, of course, what I call the infix syntax for it, because the parsing doesn't need to care whether it's actually an expression of the language or not. So that's one of the benefits of really separating those 2 parts. So now that I know how to define a macro, of course, the question is how to use a macro. Well, you can guess what it looks like. The question is mostly, how does the language determine when you have a macro call as opposed to a function call? In Lisp, usually you just look at the environment and see what's going on. Here we do something similar, but since we like static typing, we actually don't just look at the definition of the macro you're calling, or at least what is in a function position, but we look at the type. And so if the type of the first element is macro, then we decide, oh, this is a macro call, and I will try to expand it. Of course, if I do that, that means I have to be able to do type inference before I can do macro expansion. And of course, you can't do type inference without first doing macro expansion as well. So clearly, I need to interleave those two, and I do that in the elaboration phase, which does both type inference and macro expansion, just like as it is done in template Haskell, basically. I'm actually pretty happy about that because that's what I wanted in the first place anyway. So what does the elaboration function look like? Well, this is a pseudocode version of it. So I take a context as an argument, I take an S expression as an argument, which is the expression I'm trying to elaborate, and I return both an elaborated version of the code in a core lambda calculus and the type of it. And as you can see, it's fairly straightforward. If it's a symbol, then you assume it's a variable reference. If it's an immediate, then you assume that it's a constant value. And if it's something else, then you need to decide what is actually going on here. And so you elaborate the head, which will return the elaborated version of the head and its type. And then you look at the type, and if it's a macro, then you perform the macro expansion, and then you try to elaborate it again. Here, the maybe more interesting part is that I use the same approach for special forms. So just like in Scheme, I do not want to hard code the core constructs of the language with names. Instead, I define them as special forms, which are kind of special values, which can be associated to arbitrary names. Of course, initially they associated with meaningful names, so you can write normal programs, or you can rename them if you want to. That also lets you redefine via macros to give a new semantic to an existing name. Now, one of the things that is fashionable nowadays is actually to do type inference in a bidirectional way. And of course, in type I want to do the same. So, of course, because that lets us propagate type information in a more efficient way. So, the way it's usually done is by splitting the elaboration phase into two parts, an infer function and a check function, typically. In our case, this is a bit problematic because this use of special forms means that you can't really know beforehand whether it's going to be one of those forms that should be inferred as opposed to one of those forms that should be checked. So in the end, both functions look very much the same. And so instead I define an elaborate function, more or less like the one I showed before, but I lied a little bit about the type. The type of this elaboration function is not just a context and an S expression, but it also takes an optional type in case you want to check the typing as opposed to infer it. And similarly, the return value is not just an N expression and a type, but it's an N expression and an optional type. Because if you want to check its type, then you probably don't need to return the type or you knew it beforehand. And then, of course, on top of that, I define a check function and an infer function, because in practice, when I want to call recursively the elaboration function, I usually know whether I want to check the type because I already know the type, or on the other hand, if I want to just infer the type because I really have no idea what the type is going to be. Okay. One last detail about expanding macros is that the macro expansion function receives as an argument what I call an L expression. So it's an expression in this core lambda calculus. And of course, in general, this expression is just going to be a variable reference. So in general, it's not going to be closed. So just I can't directly extract a function from it. If it's a variable, of course I can look it up in the environment, but the binding in the environment might itself be an expression which refers to other variables. So I really need to check that this is actually overall closed if you follow all those variable references. And as you follow those variable references, you need to evaluate them so that in the end you come up with a closed value which does contain the actual function that you can call. And as you see, that means I have to evaluate bindings basically during macro expansion, during compilation. And I do it in a kind of arbitrary order and obviously complete. This probably sounds very messy to some of you, but I have a good reason for it. I'm an Emacs LISP hacker after all. So the thing that saves me though is that I build on people with principles who like to do things right, and so type is pure, which means that I can evaluate those definitions very freely, and they don't have any side effects, and the results can be cached. So I don't need to recompute them, and I don't need to be afraid of what might happen when I do evaluate them. Okay, I see I have a tiny bit more time, so just to give an idea of what the operator precedence grammar brings you and the kind of limits that come with it. One of the main problems I've had is that, as I said, this is a very weak kind of parsing technology. So there are some constructs that you can't express quite the way you would want to. The one that has bitten me most, or that annoys me most, is that I cannot have both of those be true of those two lines. So I want to have the type annotation x colon a arrow b be considered as the type annotation of x as being a function. But I also want to have a syntax so I can say lambda x with an annotation that x has type A, and that it returns a body, and that the body is B. But of course, that would mean that I have to parse the x and the colon and the arrow with different precedences in both cases, which clearly I'm not allowed to. So I'm forced in Tiger to have parentheses around this x colon A, and if you don't put any parentheses, it's very interesting what happens, because operator precedence grammars focus on just finding a structure to your code. And they don't really know beforehand what is the intended structure. So for example, if you write something like this, then it's just going to say, that's perfectly fine. This looks like a fine piece of code to me that basically says I have an if prefix with nothing else, and two arguments, an A, and something else which is an open parenthesis prefix, and which has as single, which carries just one value, which is this then with C and D arguments. So this is the downside of using operator precedence grammar, which of course you can solve by having a appropriate error handling in the second part of the parsing when you take a nice expression and try to elaborate it. So if you see an if underscore without then the else, you'll probably want to see, this variable has no binding, but maybe it actually could be a prefix of something else and give a slightly more meaningful error message. But it is a source of problems in the kind of error messages you can give to the user. And so I was giving this example for the case of lambda. If you don't put those parentheses around the x colon A, then it will think that you just have a lambda x, and then the rest is a colon A arrow B. And so it will be a lambda without an arrow, and it will give you an error that, lambda underscore is not bound. It's a variable that I don't know. But other than that, it works fairly well. So there are some issues that would need to be dealt with in terms of error reporting, but this is about it. So I think this is I'm going to conclude here. So I defined a language which has a very ML feel to it, with both on the syntax and semantics, and while at the same time providing a simple and powerful macro processing, just like Lisp does. And I hope this will work out to be actually practical in use. But They're still to be proven. Thank you. Yeah.
What are the types of quote and eval in typer?
Oh. So, what is the type of quotes? What was the other one? Quote and?
Eval.
EVAL.
I do not have eval. I do have quotes, obviously. But quote is a macro, so it doesn't actually have a type other than macro. Yes?
Is there a story for partial evaluation and how that fits with concurring and how that fits with the infix syntax?
No, currently not. But that's something that I hope will be coming very soon. Yes?
So what kind of syntax extensions have you played with?
Oh, currently, basically things like quotes and and basically the case analysis right now in the core is just a very simple case analysis with very simple patterns. So I'm playing with just extending it to the usual patterns, but nothing more fancy than that now. You had another question?
Yes. You have a premise that you want to do it. You have a premise that you want to do this in LISP.
Yes.
Now, is that because of the work you're doing?
Oh, most likely, yes.
Okay. So there are systems out there today, like brackets, syntax, parse. You only all these kinds of things you want here,
Yes.
but then you don't get syntax parsing with it, then actually you do it.
No, because that doesn't give independently types.
No, you have to do some work.
Exactly.
But a lot of what you said here was probably for
Yes. Yes, that's another implementation approach, definitely. Yes?
In your system, do you implement quote as another macro that you can implement, or is it a primitive?
No, it's a macro implemented in the language, just like backward in LISP. It has the same structure. Yes. Yes?
So how many stages of macro expansion can you do in this language?
Arbitrary.
So can you do macro expansion at runtime, as it were?
No. No, it's all done as a pre-processing, just like in classical LISP, because I do not have an eval function exactly.
So an arbitrary number of stages as long as they're all done on the
Right,
first
exactly.
stage. Okay.
For this meaning of stage, yes. Any number of stages as long as it's one.
Or you write your own or he could write his own macros.
Sorry?
He could write his own macros.
Yes.
Anytime you want.
Yes. But you can only use them during macro expansion, which is...
No. If you write your own macro extensions, you can do it.
But then you have to write your own evaluator for it.
Well, why not? Those are easy things to write.
Yes.
So, for something like match compilation to get coverage areas, you need the type information. Can you write macros that look at the context and get access to the?
Yes, that's a very good question. Currently, I do not have access to the context. But actually, this is why I wanted to have macro expansion be part of type inference, because I want to be able to have access to the type context, either for performing type checking or for just using this in various ways. Yes.
Okay, we should probably take the rest of the questions offline. Let's thank the speaker again.